You know, hidden inside the walls of literally every building is this incredibly complex network of electrical wires. And choosing the right one, well, it's not like picking one off a shelf at the hardware store. It's a critical engineering decision. And if you get it wrong, the consequences can be, well, pretty serious. So today, we're going to decode the rules that keep all of us safe, and we'll be using the Korean Electrotechnical Code, or KEC, as our guide.
And it's a totally fair question, right? I mean, you look at them and think, why are there so many different kinds? It seems like wire should just be wire. But it turns out every single one is a specialized tool designed for a very specific job. Matching the right wire to the right application isn't just about, making sure the lights turn on. It is the absolute foundation of electrical safety and performance.
All right, so here's our game plan. First, we'll talk about why picking the right wire is so critical. Then, we'll get into the two big concepts, allowable current and voltage drop. After that, we'll walk through a real-world example to see how it all works. And finally, we'll wrap up by looking at that classic balancing act between safety, performance, and of course, cost.
Okay, let's dive right in. At first glance, picking an electrical wire might seem pretty straightforward, right? But the truth is, the stakes are incredibly high. We're not just talking about getting something to work for a day or a week. We're talking about making it work safely for decades to come.
And this, right here, is exactly why codes like the KEC even exist. Think about it. If you use a wire that's too small for the job, it's like trying to push a river through a garden hose. It's going to get hot, really hot enough to melt its own protective insulation, which can wreck the equipment it's hooked up to. And in the absolute worst-case scenario, it can start a fire. These rules, they're designed to make sure that never, ever happens.
So how do we actually figure out which wire is the right one? Well, it all starts with the first and maybe the most important principle of them all, allowable current. You can think of this as the absolute bedrock of safe electrical design. Everything is built on this.
The best way to think about it is like a water pipe. You know, a tiny little pipe can only handle so much water before the pressure just gets to be too much? Well, a wire is the exact same way. It can only handle a certain amount of electrical current. That's what engineers call its ampacity, before it starts to dangerously overheat. And that limit? It's all about the temperature where the wire's insulation starts to melt.
Now here's where it gets interesting. A wire's ampacity isn't just one single fixed number. Oh no, it's totally dynamic. It changes depending on its environment. What's the insulation made of? Is it standard PVC or some high-tech, high-temperature material? Is the wire just hanging out in the open air, or is it stuffed inside a hot conduit with a bunch of other wires? Is it copper or aluminum? The KEC forces engineers to consider all of these things to figure out the true, safe current limit for that specific situation.
Okay, what you're looking at here is basically the heart of the entire electrical safety system. So imagine this graph is plotting heat versus electrical current. That green line, that's the wire's danger zone. If you cross that line, its insulation starts to melt. Bad news. Now look at the blue line. That's the circuit breaker. And notice the most important thing. The blue line is always below the green one. What does that mean? It means that if there's ever a power surge, the breaker is designed to trip and cut the power long before the wire even gets close to its danger point. So, what's the breaker's real job? It's to protect the wire. It's the wire's bodyguard.
But here's the thing. Safety is only half the story. You could have a wire that's perfectly safe and will never overheat, but it still might not be able to do its job right. And that brings us to the second pillar of wire selection, voltage drop.
Let's go back to our hose analogy. If you have a really long garden hose, you know the water pressure at the far end is always a little weaker than it is right at the faucet, right? Well, electricity works pretty much the same way. The farther it travels down a wire, the more the voltage naturally drops. And if it drops too much, well, that's when your fancy new equipment won't get enough power, a motor might struggle to start, or your lights will flicker and look dim. Not good.
So, to make sure this doesn't happen, the KEC sets some very strict limits. For a standard low-voltage system, like in a house or office, lighting circuits are super sensitive. They can't lose more than 3% of their voltage from start to finish. Now, circuits for things like motors and other big equipment, they're a little tougher, so they're allowed a bit more wiggle room, up to 5%. These rules are all about making sure that every piece of equipment gets the power it needs to run just the way it was designed.
All right, enough with the theory. We've covered the two big ideas, allowable current, which is all about safety, and voltage drop, which is all about performance. Now, let's make this stuff real. We're going to take the KEC and apply it to an actual common scenario.
So here's our mission, should we choose to accept it. We've got a circuit that needs to handle 25 amps. We know the wires are going to be copper with standard PVC insulation, and for the installation, they're going to be run through a conduit. That's just a pipe for wires that's buried deep inside a concrete wall. Our job?
Pick the right wire. And we're going to tackle this using a simple 3-step process straight from the KEC playbook. Step 1, we figure out the special code for our installation method. Step 2, we use that code to find the right spot in the big KEC reference table. And Step 3, we choose the wire size that checks all the boxes. Simple as that.
Okay, Step 1. This part is kind of like using a secret decoder ring. We pull up the KEC's installation table. We find the row that says Embedded in Structure, and we find the column that says Conduit System. And where those two meet, that's our code. That's the key that unlocks the next step. And when we cross-reference that, we find the official description for our method. Insulated conductors, inside a conduit, inside masonry. The KEC gives this specific setup a unique code, B1. And trust me, that little 2-character code is the key to this whole puzzle. Now for Step 2. We take our magic B1 code over to the main event, the allowable current table. This thing is huge, but our code takes us right to the column we need. From there, we just narrow it down based on what we already know. We're using PVC insulation, a copper conductor, and we have 2 current-carrying conductors in our circuit. And now for the grand finale, Step 3. We just look down that specific column. Okay, a wire that's 2.5 square millimeters thick, the table says it can handle 21 amps. Is that enough for our 25 amp circuit? Nope, not even close. So we look at the next size up, 4 square millimeters. And the table says 28 amps. That safely covers our 25 amp requirement with a little room to spare. And just like that, we have our answer. The correct wire is 4 square millimeters. So, there we have it. We've found the minimum size the code requires. But, and this is a big but, is the minimum size always the best choice? And this question brings us to a classic dilemma, one that pretty much every engineer has to wrestle with, that constant balancing act between safety, performance, and cost.
Let's break it down. On one hand, we have our 4 square millimeter wire. It's perfectly safe, it meets the code, and it's the most cost-effective option. It gets the job done. But what if we went a size up to a 6 square millimeter wire? It's going to cost more up front for sure, but because it's thicker, it will have less voltage drop. That means better, more efficient performance for all your equipment, and that can mean real energy savings over the entire life of the building. So, do you save money now or invest for better performance later? This, right here, is where engineering stops being just a science and starts becoming an art.
And this quote from the source material just hits the nail on the head. It says a smaller voltage drop is good for electrical characteristics, but increases the conductor's cross-section and reduces economic efficiency. In other words, yeah, better performance is great, but it costs more because you need a bigger wire. So the real job of the engineer is to find that perfect sweet spot, the point that meets all the technical needs, fits the budget, and above all, stays well within the safety lines drawn by the code.
So really, the next time you look at a building, will you think about all those hidden calculations keeping it safe? It's this incredible, invisible world of rules and engineering choices, this constant balancing act between physics and economics, all humming away inside the walls to make sure our world is not just powered, but also protected.